This video will cover constructing advanced formulae in your models in R. By the end of this video, you should understand how to create a formula with many polynomial terms of a feature, and you should understand how to create a formula with interaction terms of features. The code used in this video is available in the Learning Management System. The data file used is dcelectricity.rds. You should download those now if you'd like to follow along. You saw in a previous video that we were able to improve the predictions of a model by adding a square of one of the features. Adding polynomial terms of features could improve model predictions if the process that you're trying to model, the relationship between the features and the label, is nonlinear. Why is that? Polynomials do a really good job of approximating nonlinear relationships. In fact, with enough polynomial terms, you can approximate any function. Just to show this as an example, suppose I want to approximate the function y equals the sine of x. I'll try and get as close as I can with a linear model. So if I were to model this as y equals an intercept plus a slope times the variable x, you can see right around the origin, right around that 0 point, I do pretty good, but I don't do so well far away from there. If I were to add square and cube terms, you see I do a little bit better. If I added terms up to the 5th power, I do even better with terms up to the 7th power, the 11th power, and with the 17th power, it does pretty well over a pretty wide range, but then starts to diverge. And this is what I mean by using polynomials to approximate functions. Even though the sine function is very different from what we think of as polynomials, given enough polynomial terms, we can get really good approximations of this function. So how might this come into your modeling? You might often want to add polynomials of features to your models. These are going to take the form shown in this expression, where you're going to add squares and cubes of your features, each multiplied by a parameter. This can help you capture the nonlinear relationship between features and labels while still retaining a linear model that you could model with something like OLS. Polynomials can be really good at approximating other functions, and more terms allow you to approximate more complicated functions. Typing out all of those polynomial terms in a formula could be complicated. You can add polynomials to a formula using the poly function. It takes 2 arguments. The first is a variable, the feature that you would like to construct a polynomial of, and the second argument is a number representing the power, the highest numbered power that you would like in that polynomial. So including the term poly x, 5 in your formula would be identical to typing this expression here, where I include each polynomial term from powers 1 to 5 of that feature x, and it would be identical to including the mathematical terms there, x to the 1st power, to the 2nd power, and so on in my model. The poly function doesn't actually construct polynomials like the ones that I showed you. By default, it constructs what are known as orthogonal polynomials. These aren't the same as that mathematical formula. They're actually a mathematical transformation of the feature that you'd like to construct a polynomial of. Why is that? Suppose that you have a feature that ranges from 1 to 1000. You include 20 polynomial terms. The 20th power of that term would range from 1 to 10 to the 60th power. These are all valid numbers in R, but R only has 16 decimal places of precision. That means the really small numbers would be completely swamped out by the precision errors and even in double precision numbers. This can make your models very imprecise because the features vary really widely in scale. This is the reason that R uses orthogonal polynomials by default. They're going to transform your feature when it constructs the polynomial to reduce the scale issues that you might encounter if you just constructed a polynomial the way I've written it out in those equations. The predictions from orthogonal polynomials are identical to the traditional polynomials. The difference is in the coefficients. If you look at the model coefficients, they're not going to be the same as they would be if you used a traditional polynomial. If you care about the coefficients, you can switch to using the traditional polynomials with the raw equals true option. Just be aware that you might get some warnings from R if you use the raw equals true option, particularly when you're making predictions if the scale of your features are causing problems. Let's take a look at using the poly function and formulas. I'm going to load some setup code, including the data file dcelectricity.rds and the required libraries. So as my first example, I'm going to include a 2nd degree polynomial in high temperature in my model. This means that I'll include high temperature and high temperature squared. I'll run that and print the model out. You can see in the output, there are 3 coefficients: the intercept, the coefficient on high temperature, and the coefficient on high temperature squared, with that number after the poly function denoting the power to which that feature was raised. Note that I trained this model using orthogonal polynomials. So it's difficult for me to interpret these coefficients, because I don't know exactly how the orthogonal polynomials were constructed. Instead, going back to my code, if I'm interested in the coefficients, I can use the raw equals true option. This will train the model using traditional polynomials, and the coefficients will be on terms that I expect them to be on. Looking at my output, you can see I still get 3 coefficients. I have an intercept, a coefficient on the term to the first power, and a coefficient on the term to the second power. I could take these coefficients and plug them in to a polynomial model to generate predictions from this model. Going back to my code, even though the coefficients from these models are different, they lead to the exact same predictions. What I'm going to do is create predictions from each model, model.2, which used orthogonal polynomials, and model.2.raw, which used traditional polynomials. Then I'm going to create a visualization using both the orthogonal polynomial and the raw polynomial version. The raw polynomial version will be drawn with orange dots. I'll make them relatively large, size equals 4, so they show up in the visualization. And then I'll draw the orthogonal polynomial dots on top in green, slightly smaller. If the predictions from these two models are exactly the same, the dots should line up directly on top of each other. Let's make that visualization. And looking at it, you can see that's exactly what we get. The green dots from the orthogonal polynomial line up exactly with the orange dots from the raw polynomial. We're not limited to just 2 polynomial terms. Going back to my code, if I wanted to add more polynomial terms, I just change that argument to the polynomial function. Here I'm going to train a 7th degree polynomial. I'll add the predictions to my tibble, and then I'll generate a similar visualization. I won't plot out the predictions from the raw polynomial since we know that the predictions are exactly the same. Looking at the visualization, you can see that 7th degree polynomial follows the pattern of the relationship between high temperature and electricity demand even more closely than the 2nd degree polynomial did. So you saw the predictions for our model got better as we added additional polynomial terms. And you might wonder, are there any downsides to including many polynomial terms? You should be careful that your predictions might behave oddly in places where you don't have much data, and that effect can get worse as you add more terms. The example that I showed using the sine function before assumed you had nearly infinite data. But what happens if that's not the case? Your predictions can start to get very inaccurate. Suppose instead of having infinite data, I just had these 100 data points. These are randomly generated to follow the sine function, but there's a little bit of error in them as well. What I'm going to do are train models with polynomials of different degrees and see how well they predict that true sine function, which is what underlies all of the dots you see on the graph. If I use a linear function, the dark red line is what comes out of my model. The lighter red line is what I would get if I had infinite data. You can see they don't match each other very well. The dark red line somewhat predicts the relationship that we see here, but it still doesn't do a very good job. If I included 3 polynomial terms, it maybe does a little bit better following this relationship. Still not as good as if I had infinite data, that lighter shaded line. The same thing adding a 5th power and a 7th power. If I add an 11th power, you see things start to really go awry. The model that I predicted varies wildly out of the edges of the graph. It does a pretty good job in the middle, but if I were trying to make predictions around x equals 5 or -5, I might be really far off. Going all the way up to the 17th power makes this situation even worse. Now if I were to look around x equals -4 or x equals +4, I would get values that are incredibly far off from the true value of the function. This is a cautionary tale to warn you that if you include too many polynomial terms in your model, you might start getting some very odd predictions, particularly at the extremes of your data where you might not have very many observations. This is a specific example of a very general problem called overfitting that we'll deal with in some future videos. Another way you might modify your formulae are to include interaction terms. You might think that 2 features interact to influence a label. What I mean by this is that the effect of one feature depends on the level of another feature or features. Suppose I was interested in predicting energy usage by air conditioners. Air conditioner usage increases as the temperature increases. When it's hot, higher humidity also increases air conditioner use. However, when it's cold, humidity has very little impact on air conditioner use. I might have data on air conditioner use, I'll call that AC, the temperature, and the humidity. I'd like to construct a linear model of air conditioner use. So let's think about what terms I might include in that model. I could start out with this model that I have at the top, where I have that the air conditioning usage is equal to an intercept plus a slope times the temperature plus an additional slope term times the humidity. This model is going to assume that air conditioner usage will change with temperature and air conditioner usage will change with humidity. but the amount that the air conditioning usage changes with humidity is unaffected by temperature. This is going to ignore the fact that humidity only matters for air conditioning usage when it's hot outside. So how might we modify this model? One common approach to modifying models like this is to include an interaction term. That's what I have as the final term in this model, where I have an additional parameter, and then I construct a term that is the temperature feature times the humidity feature. Now this model is going to assume that air conditioner usage is going to change with temperature, it will change with humidity, and the effect of humidity on air conditioning usage changes with the temperature, and also vice versa. We're often going to model these interactions by multiplying features together. We'll call these interaction terms. You can include interaction terms in a formula using the asterisk, the multiplication operator. So in this example that I have here, my formula is the label y is a function of x1 interacted with x2. This model is going to include the effect of x1, x2, and the interaction of those features. What this is saying is that when you use the interaction operator, R is going to generate all possible interactions. What does that look like mathematically? Taking that same formula would generate a mathematical expression like the one I have here, where I have the x1 feature, the x2 feature, and the interaction of those features. R is going to construct all possible interactions when you construct formula this way. So in this example, I have the x1 feature interacted with the x2 feature, interacted with the x3 feature. This is going to give me a model where I have x1, x2, and x3 as terms, plus the interaction of x1 and x2, the interaction of x1 and x3, the interaction of x2 and x3, and also the interaction of all three features. You can see that if you construct interactions of many features, you might get a very, very complicated model. The warning you saw with polynomial terms earlier still applies here. If you start including many, many interactions in your model, you might start to get some very odd predictions, particularly in places where you don't have a lot of data. Looking at my code here, you can see I'm constructing a linear model of electricity demand with high temperature interacted with low temperature. I can train that model, we'll print it to look out at the results. Also as part of this, I'm going to add the predictions to my data table and construct a visualization. With black dots, I'll have the actual high temperature and demand data, and with orange dots, I'll show you the predictions from this model. I'll run all of that code. Looking at the model formula, you can see that there's an intercept, a coefficient for high temperature, a coefficient for low temperature, and a coefficient on that interaction term. Going over to look at the resulting visualization, you can see the predicted dots in orange, the original data in black. Including this additional information, the low temperature and the interaction of high temperature and low temperature possibly improve the predictions that we have here. Remember, what this is assuming is that electricity demand is not only impacted by the high temperature and the low temperature, but also the relationship between both high and low temperature. Including these interaction terms can allow you to make much more flexible and possibly more predictive models.